Hello everyone, so in this video I'm going to discuss about sequences where they have constructed using trigonometric functions. So particularly I will discuss about these three given sequences in the screen, okay? And at the same time let's visualize them also. So what do you think what happens in the first sequence, cosine n pi? So what are the terms of the sequence look like, for example? So if we start from n is equal to 1, so it's going to be cosine pi, right? When n is equal to 2, cosine 2 pi. When n is equal to 3, cosine 3 pi. So this is the sequence, right? Okay, so let's visualize it. Let's see what's going on. So cosine n pi, so okay, so as you can see, the values of the sequence are switching between -1 and 1, -1, 1, -1, 1. Okay, so what do you think? Is this sequence convergent? No, we discussed about that, right? Terms of the sequences does not approach to a real number. Okay, the only two real numbers that we have in this sequence is 1 and -1, and terms of the sequence doesn't approach to neither 1 nor -1. Okay, so this is a divergent sequence. All right, we want to start with a simple one. All right, so then how about the sequence pi over n, sine pi over n? So now let's visualize this because this is an interesting sequence. So sine, so there are several ways we can talk about this sequence. Okay, so if we, let's see. All right, so now here if you look at the terms of the sequence, well, they are decreasing, right? So 1, 0.8, 0.7, 0.5, 8.5, 0.43, 0.38. Let's visualize this. Okay, so it seems to be like they are approaching towards a horizontal line. Okay, let's make sure whether it's approaching. It seems to be like it's approaching towards 0. So let's make sure whether it's the case or not. So, well, let's find out visually and then we will prove it in abstract way. Okay, so if you keep a look at the y-axis, the values are getting smaller, 0.01, 0.05, 0.02. so it's like 1 over n. It's similar to the behavior of 1 over n, right? Sequence 0.01 and let's see, yeah, it's getting smaller and smaller. So let's calculate the limit using Mathematica. It's 0. So why is that? So this sequence is convergent. Now why is that? So let's look at the limit. All right, so limit, so if you want to find the convergence or divergence, we have to take the limit. All right, so let's discuss, let's try to make sense of it using a discussion. Okay, now when n gets large, what happens for the pi over n is that pi over n is getting smaller and smaller, right? Actually, so if we only focus on the part for pi over n, if we forget about sine, okay, so for n is equal to 1, it's pi. When n is equal to 2, it's pi over 2. When n is equal to 3, pi over 3. Right, so this is decreasing. So if you think in terms of degrees, this is what? 180, 90, 60, or if you think in terms of radians, it's 3.14, and half of that, 1/3 of that. So it's getting smaller and smaller. Now think, after a long time, when you write enough terms, long enough terms, n is going to be extremely large, right? Because n is getting larger and larger. So pi over n is getting smaller and smaller, getting closer to what? What do you think? Getting closer to 0, right? Okay, so think about this. Even though you have pi, 1 over n is getting closer to 0. So pi times 0 is 0. So actually inside, when n is large, inside, okay, when n goes to infinity, inside of the sine function is actually 0. So sine 0 is 0. That is where you get the limit to be 0, where then it's become convergent. Okay, now here's one thing. Actually there's a theorem. Okay, so this is a important theorem. This theorem says, now look at what happened here. Take a limit. Okay, let's discuss the theorem. after I explain this. So we know the limit is 0, right? But how did we get this limit? We discussed about the limit of the inside, right? We only focused on the part pi over n and we decided that goes to 0. Then sine 0 is 0. So actually limit of pi over n when n goes to infinity is 0. So the limit of the sine pi over n is similar to sine limit of inside. Do you agree? That's exactly what we did, right? So mathematically or in abstract sense, what we have done is we have taken the limit inside the sine function. Can we do that? Well, we can do that. There's a theorem. We can take the limit inside to a function if the function is continuous at the limit. Okay, so it's continuous at 0. Sine function is continuous at 0. Okay, so if you think about, there's no discontinuity, there's no gaps. Oops, that's not sine, right? So sine is very nice smooth curve. It's continuous, no gap, so nothing weird. So you can use the theorem. The theorem says that you can take the limit inside. That means, what does that mean? Think about what happens in the inside and find the limit of the inside and evaluate the function at that limit. So limit of inside is 0, sine 0 is 0. We evaluate sine at 0, then you get the limit 0. Okay, perfect. Alright, so let's look at another example. So an cosine n pi over n plus 1. Now let's try to solve it mathematically and then visualize it. Okay, alright, now we want to take the limit. Okay, cosine is a continuous function, but we want to find whether it's continuous. We know it's continuous everywhere, so it's not going to be a problem. Okay, all right. Okay, so let's take the limit inside. So we can take, that means let's discuss about the limit. Let's discuss what happens inside the cosine function. That means what happens to n pi over n plus 1. What do you think happens to this term n pi over n plus 1 when n gets really large? Well, how did we approach about these things, about rational function? This is a rational function, right? A first degree polynomial over first degree polynomial of n. How did we approach them? Well, we factored the highest power, right, in the numerator and denominator. Here n is the highest power in numerator, in the denominator it's n, so let's factor n. So it's 1 plus 1 over n cancel out. So it's actually behaving like, so if we do that simplification, it's actually behaving like pi over 1 plus 1 over n. Now what happens to pi over 1 plus 1 over n when n gets large? We know when n gets large, this term approach to 0, right? 1 over n approach to 0. So 1 plus 0 is 1, right? So it's cosine limit n goes to infinity pi over 1 plus 0 is 1. So it's actually pi, right? Limit is pi. So inside the limit is pi, but that does not mean the limit of cosine n pi over n plus 1 is pi. It's just the limit of the inside part. Okay, so it's pi over 1 plus 0. 1 plus 0 is 1, so it's pi. Okay, hopefully it does make sense. So what is cosine pi? Let's evaluate. Negative 1. So limit should be negative 1, and it's again convergence sequence, right? Because negative 1 is a real number. So let's visualize this. Is that the case? So what did we have? N star pi. Okay. Alright, so let's look at the table. Well, you can see everything is negative and they seems to be like getting towards negative 1, right? Approaching negative 1. So if you look at negative 0.5, negative 0.7, 0.8, 0.9. Okay, let's visualize it. Oh, as you can see, they are approaching negative 1. Do you see? So the limit is negative 1. Visually we confirmed it. Okay, so that's what going on with that sequence. So the important takeaway here is that theorem. So if the function continuous at that limit, you can take the limit inside the function, inside to the function. You can calculate the limit of the inside part and then evaluate the function. You can do it for natural logs. natural log functions at certain points. So we will see those examples in future. Okay, so this is what I have for trigonometric functions, like sequences constructed by trigonometric functions. There are more interesting sequences with trigonometric functions, but to learn them we need concepts called squeeze theorem and L'Hopital's rule. We will be learning them in future. Okay, I will do them in a separate video. Okay, all right, in next video let's learn the squeeze theorem. All right, thank you very much.